Hey guys, welcome to my group theory lecture. And so previously, I make a video about classification of finite abelian groups, and which I talk about a thing called invariance. I talk about thing called invariance. I say that every p group or the p group has some number n1 up to nk, which you can separate this into a1 time up to times ak, and each of the small singularly group with pointer p to ni, and I say these are called invariants, but I didn't tell you why. Okay, so now this video is proving another theorem, which is also very important. Okay, so I just say that every abelian group can be written as a direct sum of singulic, and particular for each prime power group, the p group, you can also do this. And but I haven't tell you that actually this invariant actually quantifies all the group, all the abelian groups. Yeah. So basically, what I'm trying to prove is the following. So this is our main theorem in this video, and so let's say G and G prime, both with order p, p to n. Okay, and G and G prime are isomorphic if only they have the same invariance. So this is why they have the same invariance. Okay, so what I'm saying is that if you can write G in terms of A1 cross A2 cross AK, and each AI has the prime power Ni, and I can write as N1 greater or equal to N2 up to greater or equal to Nk. And for G prime, I can also do the separations. I can also do the same thing. Let's say this is p to ni prime, so I get let's say I use hi. Okay, so h1, h2 up to let's say hs. Okay, so G isomorphic to G prime if only if ni equals to hi and k equals to s. So basically, it tell you that the two abelian group is isomorphic if only have two abelian p group is isomorphic if only they have the same invariance. So for example, you can easily see that. So basically, Z8 and the Z for cross Z2 or Z2 cross Z2 they are non-isomorphic. I mean, this is very easy to see if you don't know this theorem, because this guy has order 8, and there is a group element order 2, and the maximum order is 2, right? But it's not easy to see that maybe maybe if you take this guy and yeah, but basically you can you might ask whether let's say how you can what you can easily say that how you can easily determine these two of them are not isomorphic. A little bit strange, right? So, but using this theorem, that we can basically develop the systematic technology to prove techniques to prove that this is actually invariance. Yeah, so proof is a very lengthy but very interesting, and it can help you to find something which is I think is really interesting. Okay, so let's do the lemma. So in this video I'm talking about a p group. So I can define a g of s, which is all the x in the group G, which has order s. I should not say order s, I should say s to s is e. Okay, so theorem: if G and G prime are isomorphic, if and only if G of s equals to G prime of s for every s, right? So s must be some integer. Okay, and sorry, I should not even should be only these directions. Okay, so proof. This is very trivial, right? Because let's say I take x belongs to G, then I get x to the since x belongs to GS, so s belongs to GS, so s to s equals to e, which tell you that phi of x e is e, right? Because let's say phi is a homomorphism, let's say phi is isomorphism from G to G prime. So this is iso. then obviously, then by this, you get the phi of x belongs to g prime of s. So we prove that g of s is a g prime of s, and but this phi is isomorphism, right? So you can just reverse. So we just reverse and get another directions. Okay. Okay, so there's this lemma should be the very important one, which will give us the answer. Okay, so this is a key lemma. Let's say G is a P some prime P group, and let's say G has the decomposition A1 up to AK, and each AI, right, is a cyclic generated by AI, small AI, and let's say with order P to the Ni. Okay, so basically you can imagine that I have a line which N1 greater than N2 greater than N3. Okay, up to Nk. Okay, then I want to, and let's say you pick some M. Okay, you pick some M. You pick some M. Let's say this is, let's say M satisfy the greater or equal to Nk T plus 1 and Nt. Let's say M satisfy this. So basically what I'm saying is that let's say this is M, this is Nt plus 1, this is Nt, right? So M falls into some particular region, let's say this. Okay, then I want to ask what? I want to ask GPM, which is all the group, sorry, all elements such that order at most P to M. So the lemma tell you that how to quantify this group. Okay, so results will be a little bit tricky. So it will be B1 times up to BT times AT plus 1 to AK. So obviously that for T, for the group before smaller than M, this is trivial, right? Because this group, every element in its at most have the order P to the Nt plus 1. But P to the Nt plus 1 is basically divides P to M. So all these group naturally falls into the G to the PM by definition. How about how to quantify this B1 up to BT, right? So this BI is a cyclic group. Let's say with order, let's order P to M, right? This is a bullshit, right? Because it's trivial, right? Because this P to M by definition is the order P to M, and was generated by AI to the P to the Ni minus M. Okay, because N1, N2 up to Nt is greater than M. Okay, so this is also I think this is a little bit intuitive. If you don't feel intuitive, then you need to think a little bit because it's actually very intuitive. Okay, and let's say the order of this. Let's say the order of this is P to M. Sorry, P to U. Okay, so let's consider. Let's say G to the PM has order P to U because it's a P group, right? So it must be prime power. Where what? You just take U, right? So you just take U. You just take power, you get U equals to MT, right? Because these are all M. These are all LM, right? These are all the group with order M. So get M up to MT plus the rest, which is NT. Let's say NI. Don't worry. With NI, I from T plus 1 to Nk. K, right? Okay, so this is the formula where you just take the absolute value. Take the order. Okay, so let's quickly give it a proof. So after the proof, then we can easily get our first theorem that I want to prove. Okay, so obviously that by definition, right, all this falls into GM and all this falls into GM because AI P to Ni minus M, if you just take AI P to Ni minus M, let's say you take the p to the m, that become ai p to the ni, right? So become identity, right? So easy to see that g to the p to the m will eat all the a1 all the b1 up to bt, and also at plus 1 up to ak. So this direction is trivial by definition. Okay. So the rest is to prove another directions. Okay. So let's say I take x to be a1 lambda 1, a2 lambda 2, up to ak lambda k. This is by definition because x is a product of ae. Let's say I take some x, which in terms of this form, and I ask in GM. Okay. So let's satisfy xpm is e, right? Then what is spm? Right, SPM will be just a simple calculation. So A1 lambda 1 PM, A2 lambda 2 PM, up to AK lambda K PM. It's identity. Okay. Then by definition, you get everything is identity, right? So you get because this is the product, so you must have this. Okay. Okay. So so this is a condition, right? So for each, you get some conditions, right? So let's consider. So if I from 1 to 2 to k, right? This is all conditions. So if I greater than t plus 1, so what it means is that you're at this region. If you are at this region, right? Then the PM already. So p to n I already divides p to m. So everything become trivial, right? So these are all the conditions that I don't need to worry because it must be identity. Okay. So I only need to worry about when I less or equal to t. So I got p to n I divides this is my condition, right? Now p to n I is greater than p to m. So this equation is not trivial. Okay. But then you prove that p to ni minus m divides ni, right? So in this case, your ni is greater or equal to m. Right? So this, if ni is greater than m, then this equation is non-trivial, right? Because this guy is larger. So you get something this. Okay, then you prove everything, right? You get then down the I to be, let's say, vi p to ni minus m. Okay, then your x equals to a1 b1 p to n1 minus m, a to b2 p to n2 minus m. Okay, and up to a t plus 1, lambda t plus 1, up to ak lambda k. And in this case, all the lambda can be choose arbitrarily. Okay, but in this case, you just tell me that x belongs to b1 cross b2 up to bt, at plus 1 up to ak. Okay, done. Okay, and then you take order, then you get this equation. Okay, so yeah, so quickly corollary. So this corollary is I think it's very non-trivial. I mean, at least I cannot just immediately see this is true. So what is the GP? Right? Let's say you take GP to the n, then what is this GP? What is the order of P element in the P group, right? So in this case, you just choose M to be, let's say, 1, right? And then, so if M is 1, then the K must be NK, right? So you just the T must be K, okay, by the previous argument, right? Because M is 1. If M is 1, then it must be here, right? So yeah, so T must be K. So GOP will just be P to the K, okay? So for example, okay, so let's see this example. Let's say G equals to D8, then what's G of 2? So by definition, G of 2 can only be 2 to the 1, right? Because in this factorization, you only get 2. So you can easily say that it must be 0 because 0 plus 0 is 0, and the 4 plus 4 is 8, right? So you get 0 and 2, so you get 0 and 4, so there are actually 2 of them. So this is non-trivial, not very easy to see. Okay, so now we can prove our original theorem. which is this one. So basically, yeah. So this is two groups are two P group are isomorphism if only if they have the exactly same invariance. Okay, so let's go to the proof. Okay, so so this one way is very easy. Suppose two of them has the same invariance, so obviously the same invariance. So you say invariance gives you the same group. Trivial. Okay, so let's work on these directions. Okay, so if you consider, let's say, G of P and G of G prime of P, then you obviously that by this that you get P to a K, right? So it must be P to a K. Let's say P to a K must be, let's say, P to S, right? So remember that my original, let's say, G has an invariance N1, N2. This is sorted. Okay, so up to NK, and then this G prime has H1, H2, up to HS. So it must be the same, right? So K must be S, right? So this is the first one. Okay, and I know that what? I know that G of P M and the G of P prime M for every M must be the same, right? By the previous. Okay, so which you prove, which you can use the previous theorem, right? So you will truncate something, right? Truncate here. You will do a truncation. Okay, and then you can easily set that if you set the truncations, and for satisfy each M, the only way is that each of them are the same. Okay, so this is a simple exercise for you. But basically, you just use the previous theorem and cut everything, and you get an answer. Okay, and the final results, let me just mention. And these results basically trivial. So the number of non-isomorphic abelian groups with order P to the N is just let's say P is prime. Okay, it's just the number of partition of N. Okay, that's it. See you guys next videos.